Hi, welcome to my video. Now, in this video, we will be solving these questions prepared by one of the best professors, Professor Onyango. Maybe we'll be making use of these questions. Now, question number one, it reads as follows. It says to us a second order gas phase reaction of the type this A plus B will give us these products over here. These are the reactants interacting with one another, is carried out isothermally. That's important at this temperature in a bed of iron or nickel catalyst. The reactants are fed to the reactor at molar flow rate of this value over here and the volumetric flow rate of this value over here. Furthermore, the feed contains 50% of A and 50% of B. 1.1, we want to assume constant pressure operation. We have the constant pressure operation, and then we want to determine the amount of iron or nickel catalyst required to achieve 40% conversion of the reactants. And when we perform this calculation, we must start from the general mole balance equation and show all steps. The moment this is indicated, that means we have to derive the equation before we can perform our calculations. So before we get to the complex part of this question, as much as it is indicated over here, start from here. Let's firstly start from there before we can complicate our lives, right? So now what's happening over here is we have a packed bed reactor, and then we have the substance that is going into the reactor, and the reaction will take place, and the substance will most definitely leave out of the reactor. Now, which substance it is going into the reactor and leaving out of the reactor? We have the chemical reaction over here, where we have two reactants, which is A and B. So between these two, since we are given two of them, it's important that we take note of which one it is a limiting, which one it is in excess. Okay, so most of the times we use a limiting reactant. Now in this case, we really do not know. We just have to work with an assumption first, right? So in this case, I will take my A to be a limiting reactant, right? So we have learned on how to determine a limiting reactant and the one that is not a limiting reactant. We know we get the negative. We did this on chemical engineering reaction 1. So now in this case, I will assume that I start with an assumption. Like I said, we're going to start, this is 1.1. We're going to start from here, deriving the formula first, and then we'll get to the calculation part and break down the information that is provided to us. How are we going to make use of it? So for now, we are most definitely going to assume. What are we going to assume? A is a limiting reactant, okay? So we assume that A is the limiting reactant. So sincerely, we want to solve 1.1. Like I said, let's start from the GMBE. So we start by looking at step number 1. You write step number 1 nicely, and then you write your general mole balanced equation, right? So the general mole balanced equation for this chemical reaction over here, since we assumed A to be the limiting reactant, we have the flow that goes into the system, which is denoted by F sub AO minus F sub A. This is the flow rate, the molar flow rate that leaves the reactor, plus the integral of what is changing, the variable that is changing, it is mass, which is denoted by W. um, Rate of reaction, we put a prime on top to indicate that this rate of reaction, it is by a function of a weight of a mass, and then we have dW, right? This is the reaction, is equals to our this is accumulation, dNA divided by dt, right? So this is the general mole balance equation, and I will call this equation number 1. Now, after doing this, what we're going to do is we consider this general mole balance equation for what type of reactor, for a packed bed reactor. So meaning we will be considering this for a differential length or differential mass, right? So we consider differential mass, right? We will consider the differential mass for this type of reactor, which is called PBR. Okay, so we consider the differential mass. In short, I don't want to write the long what. I'll just say consider differential mass. So you draw your diagram nicely over there to show that um this is your packed reactor, and then you have the material that is going into the reactor, and the material will be leaving out of the reactor. So this side, remember that we have the mass initial and then we have the mass final, right? Let's change in W, and then here we have a differential mass, which is denoted by delta W. So recall that this side we're going to have F of A W, this side we're going to have F of A W plus change in W, right? And then again, we will assume a steady state. Assume steady state. If we assume a steady state, that means the rate of moles will definitely be equals to 0. So let us rewrite this general mole balance equation in terms of differential mass. So now initial, we're gonna have this guy over here, which is F sub A, comma, W, subtract F sub A, comma, W plus change in W. And then over there, we're gonna have plus rate of reaction with mass of a catalyst multiply by change in W. And then this will definitely be equated to 0. Okay, so this is still the general mole balance equation in terms of differential mass within our packed reactor. So I will call this equation equation number 2, since we have established that this will be equation number 1, and I will call this equation equation number 3. Now what I'm going to do over here is I will try to separate these variables in such a way that I will be able to introduce the limit onto this equation. So what I'm going to do is I'm going to take this, which is the final value, which is the bigger value, which is the final value. I'm going to write it like this as a positive FA dot comma W plus change in W. Then this one will write it as negative minus FA W, and then when I transpose this on this side, it's going to be negative, but because I have already factorized negative outside, then that will be positive, even though I take it to this side of the equation, because negative and negative will divide each other. And then I divide both sides by changing W, because that's the one that is changing, and we can see that even here, the flow rate, it is the molar flow rate, it is also changing. That's why those variables that changes, I put them on one side. So here I'm going to have FA W plus delta W minus FA W divided by delta W. Then this side I am left with my rate of reaction. And where I do have change of substance, this is a constant value, it doesn't change. We can see that W is noted by delta, meaning it is changing. And we can see here we have final and initial. Definitely this is also changing. And then on this side of the equation, I will be starting by introduce what? Limit. So meaning limit as change in W tends to approach 0. And then now I'm going to have a differential equation. So at the top, I'm going to have df sub A divided by dw is equals to my rate on this side of the equation. And then this equation, it is now called the design equation, just like how we did under the PFR, the CSTR, as well as the batch reactor. So this is the design equation, and I will call my design equation equation number 4. Right? So now after deriving our design equation, this will make a step 1. And then when we consider moving to step number 2, this is what we are most definitely going to do. For step number 2, we do have the design equation now from general mole balance equation. And then now what are we going to do? We're going to talk about the rate law. The rate law. Now, if you have a look at this, what we did over here, it has nothing to do with the information that is provided, except that we know what it is. It is a PBR, right? Packed reactor, and there's a bed reactor. Besides that, we know this is we just derive this without depending on the information that we see over here. But now when it comes to rate law, it's important to understand what order of equation is this. Is this the first order equation? Is this the second order equation? Or they will give you some other hints like elementary reaction, things like that. So we are definitely told that we have a second order reaction, right? Which is a gas phase, yes, but we have the second order reaction. So we know that the rate law, it is written by negative R prime A is equals to K, even the rate constant, we denote it by prime at the top, multiply by concentration of what? Now, this is the second order reaction, and we have two species. So that will be given by concentration of A multiplied by concentration of B. This is how we write the rate law for this case over here. Okay. So from here, you are fine. You can leave it like this. Or you can also consider the fact that substance A and B, they are both equal. Since here we were told that their molar flow rate is 12 kilomoles per second, and we were also given the what? The percentages, the percentages for each of these guys. They said furthermore, the feed contains 50% of A and 50% of B. So that's literally tells us that concentration of A, it is definitely the same as concentration of B. So you can say concentration of A is equals to concentration of B, and then this will give you Ca squared. But then if you are not, or if you don't want to do it in this way, for now, it is still fine. We can leave it here, okay? Just to follow the protocol. It will work out as we go or as we continue further. Then step number 3, now we are heading to, oh, by the way, this is equation number 4, and then this will then be equation number 5. So now we are heading to step number 3. Now on step number 3, we are focusing on stoichiometry. Okay, then I focus on stoichiometry. Now, to make things easier for yourself, look at your design equation. You want to change the differentials. So in order for you to change the differentials, you have to focus on the molar flow rate of A. So now we know that the flow rate of A is given by what? It is given by F of A initial multiplied by 1 minus X of A, right? By conversion. If we introduce f of A in terms of conversion, this is how we're going to introduce it. This is what you have done from chemical reaction 1. Unless otherwise, you can leave your comment under the comment section below. If you do not understand, I'll explain how we got here. And then now this then will be equation number 6. Then now what I'm going to do is I'm going to differentiate this equation in respect to x, okay? Because x is a conversion and it is the one that is changing. And then fa sub ao, this is a constant. It doesn't change at all. It's remained the same because that's what you initially started with. So, but the conversion, it changes as reaction continues. So that's how we derive in respect to x. So even here we're gonna have dfa derive this side with respect to x, and then this is gonna be constant, it's gonna be 0, and then this one will give us negative FAO multiplied by dxa, right? Then this is the equation. I will call this equation number 7. So we go back again to our design equation nicely. We can see that we have dW. So This one is what we will do at towards the end when we are heading to the final derivation. So we have RA. RA, again, it is given by what? We just spoke about it, that it is a rate law. It is given by the concentration. So you'll have to focus on your concentration for A and B. In this case, when we want to calculate the concentration of A, making use of stoichiometry, what are we going to do? This one, I will elaborate more on it so that you understand how we got onto the final derivation. So CA, number one, in this case, we're going to say is equals to flow rate of A, molar flow of A, divided by volumetric flow rate, right? This is what we know. Chemistry, this is the stoichiometry. To calculate the concentration, using number of moles divided by volume. But in this case, if you do have a look at our information provided over here, we have no information about FA, right? It is true that we have the volumetric flow rate, but we have no information about FA. So in this case, what we're going to do is, by the way, the volume, it won't be the constant volume. The volume will, the volume will be affected, okay? The volume will be affected. Why? Because we have a gas phase reaction. So the volume won't remain the same throughout unless if we did have the liquid phase reaction. So this volume, it will look like this. It will be volume in this volume is equals to this volumetric flow rate is equals to this V sub naught multiplied by 1 plus alpha multiplied by x of A. Here we're going to have P naught divided by P multiplied by T divided by T naught. So you see, this volume, it won't be the same as volume. It will be affected by pressure, it will be affected by temperature as well as conversion when we have a gas phase reaction. Do you understand what I'm saying? So that's what is going to happen. But now if you do remember, because we're doing 1.1, now this is where I'm going to make use of the information then. They said we have to assume that we are dealing with a constant pressure operation. So meaning this pressure and this pressure will be the same. No need to indicate this when we are talking about the volume. So meaning volume doesn't get a volumetric flow rate, it doesn't get affected by the pressure. So we cancel this one out. And if you do remember again, they said to us, this type of reaction is carried out isothermally. So that literally means that T is equals to T sub naught. Again, we're not going to consider this factor. At this point in time, we are only going to say our volume, it is given by this value over here. So, meaning again, we know that F8 is denoted by this equation when we introduce the conversion factor. So we're going to have FAO 1 minus x of A divided by our volumetric flow rate. It will be V sub naught 1 plus E multiplied by x of A, right? This is still the concentration of A. But now again, if you have a look at this flow rate divided by volume, this will definitely give us a concentration of AO. Okay, it will give us the concentration of AO, or we can leave it like this. It really does not matter because we do have the molar flow rate initial for both species in total, and we do have the volumetric flow rate. So basically, when you do this, you have to understand what you're doing and how you express your equations. If maybe you want to follow the procedure on how you used to do it, then that shows you do not understand. We can leave it here, or you can convert this, because again, when you perform your calculation, you'll have to come back, change these equations once more again. You understand what I'm saying? So we can do it as traditional way. We have 1 minus x of A. Now here's the thing. If you have a look at our epsilon, which is E epsilon, our epsilon, it is given by what? It is given by the sum of the products subtract sum of the reactants. Now, the stoichiometry, we use what? Sum of what? Of the stoichiometric coefficients. So here we have one, here we have one, here we have one, we have one. This side we have two, obvious. When we add them, this side we have two. So it's gonna be 2 subtract 2 is gonna be 0, and it will affect the whole thing. And then 1 plus 0, it is still 1. So anything divided by 1, it is still 1. So definitely our concentration of A will be given by this equation. Okay? What about the concentration of B? Like I said, from step number 2, I left this as it is. I said it's fine. You can say CA is the same as CB, and then you're going to have CA squared and deal with this thing alone. But then if you still do have CB over there, then let's talk about CB over here. But then CB, it is still the same way. Let me take you through it. So CB in this case is going to be F of B divided by the volumetric flow rate is equals to, now recall that when you want to calculate the CB remaining using your stoichiometry, what you do is you have to say FB sub O subtract, you look at your balanced equation, you see there it is 1, your stoichiometric coefficient is going to be 1, FAO, right? Multiply by what? By conversion factor, divide by, recall that we say this is a gas phase reaction, and your volumetric flow rate will definitely look like this, but we won't include those two guys. So it's going to be V sub naught 1 plus epsilon XA. So now, stoichiometrically, this is how we know we calculate the molar flow rate of B remaining in a remaining, right? So now in this case, I said to you, it's either you look at it in this way, the concentrations of A and B at this point in time are the same, or you can simply say the molar flow rate of A and B are the same. So meaning this FBO is going to be the same as FAO, right? Because we have equal number of everything initially. Do you understand? So in this position of BO, I can write AO, of which now is going to look like this when I take out the common factor. So at this point in time, CB will be the same as that equation, which is CAO 1 minus XA. So I wanted to derive this to show you that it does make sense without writing it. So from stoichiometry part, this is the equation that we have, number 7, and this is the equation that we have, I'll call it number 8, and this is the equation that we have, I will call it equation number 9. This is what we have now from the stoichiometric part. And then after dealing with the stoichiometry, then where are we going? Where are we going to step number 4? Now, step number 4, most definitely, what are we going to do? We're going to combine all of the steps. Combine all steps. How are we going to combine them? Let's go back. Now, you start firstly by looking at your design equation. You see on this place of DFA, what are you going to write? You're going to write equation number 7, meaning negative FOA dxa. So we have negative F sub AO dx sub A divided by dw, we write it as it is because we did nothing on it. And then on this side of the equation, we said that on our design equation, this is the rate of reaction. But now, remember, we said that the rate of reaction, which is negative, is given by this equation, which is KICACB. Again, we have already spoke about CA and CB. We said that CA and CB are equivalent to these expressions over there. So meaning in this case, then I'm going to have, I don't think I'm going to have enough space. Let me write it here at the bottom. I'm sorry about that for your inconvenience. I will erase that. Erase this one. I don't have space there. All right, let's go. So this will be given by negative K alpha, this thing, breaking prime concentration of A. We said that the concentration of A is going to be CaO 1 subtract XA, and then we said that the concentration of CB will be the same. It's going to be CaO 1 subtract X of A. Yeah, you see, sometimes you won't get it like this because of it depends what you did here and what you did there. But as long as you understand, you should understand what you are doing. And then we divide both sides by negative. And then on this side of the equation, I'm going to cross multiply. I'm going to have dw multiply by k prime. These guys, when I multiply them, I'm going to get my CAO squared 1 minus XA squared, close the bracket, is equals to FAO dXA. And then now what I'm going to do is I'm going to make my dW the subject of the formula. So to make it the subject of the formula, I'm going to have my FAO divided by K prime CAO squared. It's fine. Let me just write it. 1 minus XA squared dXA. Right? So this is step number 4, which is combination of all the steps. So now we are deriving. I told you this is all about derivation, right? And then here I'm going to derive my W from 0 to W. This will give me W. And then here I'm going to derive as well from 0 to XA. So gonna have FAO divided by K CAO squared integral of 1 over 1 minus XA squared dXA 0 to XA. So now how am I going to integrate this? Look, if you know how to integrate it by just looking at it, it's fine. You did your engineering mathematics, you know how to integrate. Now you are doing the application of mathematics. But if you want me to help you, let me help you through how to integrate this using your U substitution. So if you want to integrate that using U substitution, remember we want to integrate this from here to here. Um, we have 1 over this dxa. How to integrate something that looks like this? I will use my U substitution. I'm going to let U to be equals to 1 minus XA. This inside of the bracket, I'm going to let it to be equals to this. And in this equation, I'm going to derive it in respect to X. So I'm going to have du negative dxa. So I'm going to have negative du dxa. So now I can see that this will be the same as, let me show you, 1 minus XA squared dxa. Now this will be the same as the integral of where I see u, where I see 1 minus x, I'm going to write my u, right? So I'm going to write my 1 over u, which is to the power of 2. And then where I see dx, which is this, I'm going to write negative du. I'm going to write my negative du, but let me take that negative outside of the integral sign. And then now, how am I going to integrate this? The bounds matters at this point in time. My bounds over here, I will be integrating from 1, listen to me carefully, not 0. I will be integrating from 1 to u. Definitely you want to understand, why am I integrating from 1 to u? I'm integrating from 1 to u because recall that if you have your packed bed reactor like so, right? So now in this case, what you want to do is your u over here, you want it to be equals to 0, and your u at the final stage, you want it to be equals to u. So how can I make my u to be equals to 0? Now, if you take your lower bound, which is 1, and then you substitute it here, where is your x? So it's going to be 1 minus 1, that will give you 0. Then when you substitute u over here, it will give you the very same equation, which is the one that we see over here. So that's why we integrate between 0 and, between 1 and u, because 1 will automatically give us this to be 0. Do you understand what I'm saying? So now let us integrate this. Make sure that your integral skill is on point. U to the power of -2 du. When you integrate this negative will die off because we're going to have to divide by -1. So we're going to have u to the power of -1. Our upper bound is u, and then our lower bound is 1. And then in this case, what then are we going to get? We're going to say this upper bound, 1 over u minus 1 over 1, because we have to substitute 1 where we see u. And then we're going to have, what's this? Add these two fractions together. We're going to have 1 minus u divided by u. Then let us do back substitution. We said that u is equals to this. We substitute 1 minus where we see x. We're going to write our 1 minus xa divided by 1 minus xa, right? Quickly, I'll just finish it up over here. Then we can see that the integral of 1, this is equals to, we have 1 minus 1 plus x of a divided by 1 minus x of a. Just doing it step by step so that you don't get confused. And then we have x of a divided by 1 minus x of a is equals to that. Okay, so going back to our question, what is the integral of 1 divided by 1 minus 1xa to the power of 2? So some people, they know it will be equals to this without deriving it, without proving it. It is still fine, because sometimes you don't understand what you're doing. It's important to at least try to derive it until you get to the answer, okay? So meaning we're gonna have w is equals to FAO divided by K CAO squared multiply by x of a divided by 1 minus x of a, close the bracket. And then from here, then we are done with our equation. Now we can solve 1.1. Okay, now how are you going to solve 1.1? This is how we're going to solve it. Now we need to pay attention to what is given, what is not given. Let's talk about FAO. Are we given FAO over here? They say to us the reactants are fed to the reactor at the molar flow rate. What is this value over here? Is this FAO or FBO? This is the total, because they are not telling us this is for A or B. Do you understand? So this, it is called FTO, which is FAO plus FBO, the total for our reactants. Okay, sharp. And then here they say, furthermore, the feed contains 50%. The feed contains 50% of A and 50% of B. Then the question is, how can we calculate FAO and FBO? So to calculate so now we're gonna do calculations. Let me start it there. So FAO is equals to the composition, which is 50% of A, multiply by the total. If you forgot, this is like from how you did your engineering, you know that to calculate the composition of something, you're gonna say something divided by total, that will give you composition, meaning FAO divided by FT, this will give you your composition. So in order for you to calculate FAO, you have to cross multiply, and then it will give you this equation over here. So now, what is the composition of A? It's 50%, which is 0.5. And then the total, it's 12 kilomole per second. Then when we punch this on our calculator, this definitely will give us half, which is 6 kilomole per second, right? Then we are done. If you want to calculate FBO, of which in this case it is unnecessary, because this is how we treated our equation, unless or otherwise if we go to this step over here, if you go to this step over here, we didn't even want to change this thing. It will still be fine, but sometimes it will be untidy and it will confuse you. So it's okay how we did it. So this will be FAO. You don't need FBO, right? But FBO will also be 6, of course. And then now, let's talk about K here. This, it is given. Now, let's look at the units. We can see that here we have moles, and then here we have kilomoles. So it's either we convert these units from moles to kilomoles, or we convert these units from kilomoles to moles. That's very important because you cannot cancel things that are not in the same standard units. Very important. Okay, so let's convert this into kilomole. So to moles, we have to multiply by 1,000. So this will be, let me see, kilo. Yes, we multiply by 1,000. This will be 6,000 moles per second. Since well, we do have moles over there. That's very important. And then seconds, we have seconds there sorted. And then now, let's talk about CAO. How to calculate CAO? Like I said, if you wanted to leave your equation like this, what is it? I want this part. If you wanted to leave your equation like this, FAO divided by V, it is still fine. We were just only, but because we converted this into concentration, then we have to go back to this equation to calculate concentration. You understand? Like, that's why I said to you, you need to understand what you are doing. So now concentration of OA is gonna be FAO divided by volumetric flow rate. So we have 6,000 over there. Now let's have a look at the units of our volumetric flow rate. Where is it? There it is. It is given to be 0.3. So this definitely will be 0.3 meter cube per second, second. So we are sorted. So let's divide that. We're gonna say 6,000 divided by 0.3. That will give us 20,000. This will give us 20,000 what? Moles per cubic meters. That's our concentration. We are sorted for this guy. And then what about the conversion for 1.1? It was given that it's 40%. Then all we are left with is to calculate the final answer. To calculate the final answer, we're going to say weight is equals to, where am I writing FAO again? So our FAO, it's given to be how much? Let's go. We got it here, it's 6,000. So we put our 6,000 over there, divide by our K. How many zeros? 1, 2, 3, 3. So we have 0.123125, and then the units are on point. We don't have to worry about that. We checked everything. The units are on point. That's very important to get the correct final answer, of course. You can make everything correctly, but then your units will not give you the correct answer if you're not careful about that. And then the concentration of AO is 20,000. We put our 20,000 right over there. And then squared, let's not forget squared, which is this, and then our conversion is 40%, which is 0.4 divided by 1 minus 0.4. Then let's put this onto our calculator to get the final answer, which is the mass of our catalyst. So we say 6,000 divided by 0.000125, 20,000, 123 squared, open the bracket, 0.4 divide by 1 minus 0.4. We close the bracket and we get the answer to be 0.08 kilograms catalyst. So then this will be the final answer to this question. And thank you.